Hi, I'm Tiani, and today's session we're going to focus on engineering economics and cost analysis. Specifically, we'll be discussing how to choose the best alternative in terms of project evaluations and investment strategies in engineering projects, as well as some other analysis techniques. So specifically, we want to talk about today and shed some light on how to do incremental analysis when comparing alternatives. We'll be looking at spreadsheet solutions as well as graphical solutions and elements of comparing mutually exclusive alternatives. What do we do? How do we handle situations when the alternatives do not overlap at all? They're distinct and exclusive. We'll be doing a set of challenger-defender comparisons method, and then finally discussing how to choose the best analysis method for our economic strategies. We start off with a vignette example. If we look at roadway constructions, many times there is trade-offs in terms of materials, engineering design, and planning. Specifically, we have a situation here or an example that deals with identifying material that we might want to use for a construction project, namely deciding between rigid concrete and flexible asphalt. What initial cost and what are the rehabilitation and costs that follow for each alternative? Asphalt, we know, is quite smooth and nice and quiet, but we also know that asphalt doesn't last as long. It's subject to rutting and shoving. Concrete with proper design lives up to 40 years. Asphalt, you might get 10 years in longevity. Further, there are more pavement and overlay choices available now in the market. So selecting the best pavement might involve discussing who is using this material. Should transportation agency be indifferent about these two materials? Probably not. Why not? What engineering economic principles should we apply to this kind of analysis? What's the most effective measure for publics to consider or public forum? How can the payment life cycle be used in choosing the right payment type? What about considering initial versus full life cycle costs? Does that affect the choice of payment material that we might select? What are the uncertainties? What are the uncertainties in estimating? What are the uncertainties in the weather patterns that might affect these materials? If federal money is significant share of initial, how might this distort decision-making by the state agency responsible for the rehabilitation costs? So what does mutually exclusive mean when there are multiple alternatives? Does that mean you must do it all, or that you can do as many as you like and have the money for? Or maybe you can do at most once. Maybe it's because they're expensive alternatives. What do you think? Well, mutually exclusive means, in the context of multiple alternatives, that you can do at most once, meaning you cannot do both. You have to pick one. It's not a hybrid, it's not a and, it's an or. Choosing the best mutually exclusive alternative requires a bunch of steps, a concrete process. You identify, first of all the alternatives, right? You need to have all the alternatives on the table with a lot of information and data. You need to build some financial calculations that include net present value, the equivalence, analysis, perhaps a graphical representation to show all the alternatives, You've got to compare apples to apples. You got to plot them on the same axis, right? Same unit of cost, same unit of measurement, same time. Then you figure out the best value, which alternative is best over each of the range that you're talking about. Time horizon, for example. Determine intersection points, and then create some analysis. We use a choice table, for example, to lay out the choices and make a selection. So if we take an example for a graphical solution, take a look at this particular example. You have cost, a range, say, right? High and low. Capacity, you've also got a range. Life cycle, you might have a range. In this case, it's the same. We standardize, right? We know that this investment is a 5-year investment. So the highest present worth or value, PW or PV, is best. So we look at the choice table, we see based on the graph, we graph this data essentially, right? We calculate the IRR. And we create a choice table. We can also do this analysis, and our preferred course is to use Excel or a spreadsheet solution. Lay out the high and low and solve for the interest, right? You can see for the high and the low and the range is the difference. The difference between high and low is the delta. If we look at another example where the machine costs are varied, we also have a salvage value here. That means there's a residual value, right? At the end of the life cycle. Notice in this example, between two alternatives, say machine X and Y, the years of life are different. One's 6 years, machine X is 6 years in duration, machine Y is 12 years. If we look at this analysis graphically, machine X has a better present worth, right? We can create a choice table. We can graph and linearly look at the results. Take another example, but you use equivalence here instead of present worth method. The EW, or rather equivalence curves, are closer to than for the present worth. This is a much more of a straight line. This is much more curvature. Same data. And we can look at this graph in a rather than graphically, we can look at it in Excel, and we can use goal seek to find the interest rate with zero difference. Cell B13 in this case contains the interest rate, same as the equivalence values. If we look at yet another example graphically, this one has the brass and stainless pipe. This time we're also looking at titanium. So 3 different materials, different life years. Titanium, as we know, has a better life, but it's costly. Is it worth it? Well, we have to look at the lowest equivalent value is the best, which means when you equalize the values, create them on an equivalent path, what's today's lowest cost would be worth it because it factors in the life and the current cost or the initial outlay, right? And we can see that brass comes out ahead in this case. We can do this analysis in Excel. Love for you to have to pause here and try Excel, recreate this example so you understand the mechanisms. We have a graphical solution for this example. 3 machines, X, Y, and Z, 2,000, 7,000, 4,250. You have different annual, uniform, but different across the options, and also different useful life. Here, we've got several choices. We've got the do nothing choice. We've got machine X, machine Y, or machine Z alternatives. Okay. Same analysis in a spreadsheet. Setup, solving for PMT, and then solving for I, which is the interest rate. So incremental analysis is across the board on all of these methods, whether you're using IRR, equivalence, present value, etc. The difference between lower cost is the incremental. The defender is the best alternative identified so far. The challenger is the next higher cost alternative, right? So we have a defender and challenger concept, and you need both. You need at least one challenger and one defender. You may have more. You may have more, but you need at least one of each. Here's an incremental analysis using pairwise comparison. Several machines that are, or several alternatives rather, that are, and they could be machines that are varied in initial costs as well as the annual benefits, right? So they generate different benefit amounts or different annual benefits, right? Obviously, because they're not all the same products or the same investment alternatives. So if we want to do pairwise comparison, we first rearrange the alternatives in the order of cost, either increasing or decreasing. In this case, we've used it increasing, or we've shown it increasing. You can see that D ranks first because it's the cheapest alternative, followed by B, followed by A, followed by C, followed by E. The uniform benefit also, notice, is incremental according to the same benefit. Secondly, you calculate the internal rate of return of the least expensive alternative to see if it's better than the do nothing at a particular interest rate, let's say 10%. If you calculate present worth by way of Excel or the formula, you're going to get 0. The internal rate, you're going to get 9.94. So what that means is, what that tells us is, do nothing is still preferred and is still the defender. The third step is to calculate the internal rate of return for the next alternative. So you do this pairwise. This is the way the pairwise comes in. And that shows you that alternative B is preferred and is the new defender. So B is better than D. The fourth step is calculate the IRR, the delta IRR of the next alternative, A over defender B. And we find that alternative B is preferred and is still the defender. We keep going. We see that alternative B is still when we compare to the next alternative, C. And finally, E, alternative B is still preferred and is the final selection, therefore. So we pairwise, 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 pairwise come up to the fact that the best solution is B. Because incremental analysis can only be done between two alternatives. And you have multiple, you have to pick the best of the two, then pick the best of the final two, and it's sort of the best of approach, right? And intuitively, that's the best way I can explain incremental analysis. I encourage you to review these slides again to see the steps that we took to decide on B being the best alternative using the pairwise comparison method. Okay, so choosing the alternative method, the optimal alternative method, if MARR is known, then we take present worth or equivalent annual easier. That's much easier to do than the IRR method. If MARR is not known or not known precisely, then the graphical approach to creating the choice table might suffice. I always like using the spreadsheets to be very sure. Graphs are a little tedious for me personally. However, graphical approaches are visual, so they explain a lot in a very concise way, perhaps really easier to explain to executives and management in a company. But it's a matter of choice. It's a matter of how much detail you have, which approach to choose. Rate of return is almost always, I would say, almost always easier to explain, provided you have the data to do that, right? Many firms have standardized on rate of return analysis, okay? You see that being used most often. Now, if we want to look at other methods of analysis, here are some of the ones that are really top of mind. You have future worth analysis, you have benefit cost ratio, as the name implies, you're looking at a ratio between the alternatives in terms of what the benefit and the cost is, and the best ratio wins, right? Payback period is how soon can you recover your investment. That's also a wonderful analysis used selectively. Sensitivity and break-even analysis is another popular method. Doing graphs using spreadsheets, and then you can also in spreadsheets do what-if analysis using various automation techniques in the spreadsheets functions that are offered. Let's look at a few. We're going to look at payback period. We're going to look at some sensitivity analysis. We'll take a look at an overview of worth analysis, and we use spreadsheets to examine some of these techniques. Take an example. Let's start off with an example. I always like to start off with a vignette. This is a vignette of a clean and green use case. We know today that buildings in the United States account for 75% of all electric consumption. Amazing. 45% of energy use is being used by buildings, corporate buildings on a large part. Therefore, high percentage of CO2 emissions, a lot of the raw materials that were used worldwide are used because of buildings and in building those buildings themselves and maintaining them. And also 13%, give or take, of the potable water consumption. So a lot of man-made and natural resources are being used by buildings. That's why we have a big movement for what I call clean and green. Environmentally friendly construction materials and methods are always being researched and tried to be used by designers and engineers, okay? They have to evaluate the costs, obviously, but there's a strong push and tendency for building suppliers and building management folks to use eco-friendly materials as well as processes. We know a lot of advantages, inherent advantages of using these green building architectures. They improve productivity, they reduce health and safety costs, they improve environment, right? Breathing environment, safety, etc. They also reduce energy and maintenance costs. Management loves that. Stockholders love that, right? Costs long-term are lower. Sometimes we think it costs more, but it's not really the case if we do a good analysis. We're finding if we do a complete analysis, it's not necessarily expensive when you look at the long-term benefits. So in order to demystify, right, or refute the myths that are out there, we have to do cost analysis accurately to show or to test whether eco-friendly costs more or less. Future worth analysis, for example, discusses alternatives and evaluates alternatives to compare them for the future. We've till date only talked about conducting present worth analysis, but future worth analysis emphasizes what the end result is. What's the final outcome? What is the end result, not what it costs now? So it's an interesting way, different way of looking at investments and alternatives. If we look at an example, a 20-year-old quits $35 a week smoking habit. If the savings account is paying 5% compound semi-annually, what does he save by the age of 65 if he stops smoking at the age of 20? Work week habit costs $7 a day. What if the $2 a day alternative substituted 4 days a week, right? Are we going to be happier? How much money are we going to save? Well, anyway, this is how you do the analysis. Use the FV function, which is the future value function, instead of the PV function. And determine, in the first example, for instance, this 20-year-old would have saved just short of $300,000, given a particular interest rate of 5%. So easy analysis. We talk about future instead of current in this kind of analysis. Here's another example. I'm not going to drill this further. You can go through this, pause the video and go through this. It's a new plant versus remodel example. And you can see that future worth is more for the remodel than it is to opt for a new plant. If we look at benefit cost ratio, we want to make sure that an acceptable alternative satisfies this equation, namely the ratio B over C, benefit over cost, has to be greater than or equal to 1. Why? Because that means the benefit outweighs the cost, right? That's the only way the ratio would be greater than 1. If it doesn't, that means the costs are higher than the benefit. It probably does not make sense by way of benefit cost ratio analysis to opt for that alternative. There might be a better alternative. Here's an example. I'll let you go through this. This is pretty straightforward. You can go through this on your own. Some use cases where this might be useful. Here's the criteria for when you use ratio analysis. Here's a benefit cost ratio analysis example, looking at 2 devices, potentially. One has a $10,000 initial investment and the other has $13,500. Useful life is 5 years, or period of comparison is 5 years. We see that B over C is greater in A, which is 1.23. That means A looks like a better alternative, more benefits for relative to cost than the other alternative. Here's another example. This one is multiple investment. You can do incremental analysis using this, very similar to the other incremental analysis that we discussed. I'd like you to take a look at this slide more carefully by pausing and examining examples. Pretty much straightforward, simple math, just to evaluate options. Let's go for a new public swimming pool, shall we? If a pool cost a little over $1 million, $1 million to build and $200,000 a year to operate, we benefit from it by $450,000 a year. If we use equivalent annual values at an interest rate of 6% with a period of 25 years, what is the benefit cost ratio? Is it 1.53? Is it 1.81? Is it 2.25? Is it 4.79? Or is it, well, it's 1.53 if we use the actual, equivalent costs and equivalent annual benefits. You can do that, obviously, on a spreadsheet as well. You'll come up with the same answer. There's a graphical representation of what's going on in the case of a benefit cost ratio analysis. And you can look at the lines to determine optimality. There are a few variations on benefit cost ratios. In the public sector, we're talking about generally all of the consequences to everyone in society or the public divided by all of the consequences to the sponsors or the government. The benefit in the case of public sector analysis is not only the tax revenue that goes towards projects, but what is the benefit to the public, right? Which might be more vast if the investment opportunities are positioned correctly. In the private sector, it's slightly different. It's all consequences except the first cost, right? And the project's first cost is the cost that is in the denominator. But the criteria for evaluating is the same. You set it up a little differently because there's a public service or public benefit versus a private benefit. But when you set up the formula or the correctly, the ratios have to still be greater than 1 to justify the alternative. But they are totally consistent in terms of the way they're calculated. Here's a government example. Again, it is, we talk about it government versus private, but the only point here is when you calculate benefit for a government project, the benefit, be careful that you're not undercalculating or underestimating the public benefit. Or alternatively said, select alternatives that have maximum public benefit, right? Essentially for little relative costs. Payback period is another wonderful technique that's used in engineering cost analysis. What is the payback period? Well, very simply, it's the time required for the project's profit and benefits to equal the project's cost. It's quite an approximate method because it projects out in time and many things can change, right? Between now and the future. So one of the direct disadvantages is that it tends to ignore the time value of money and it ignores all the cash flows after the payback. Well, once the payback period is achieved, what about all the other benefits or the costs or whatever that follow? It doesn't take that into consideration. It only focuses on the amount of time it takes to recoup the investment. If you do the payback method, it will not inherently necessarily agree because of the definition we just discussed, because of how payback period is considering the investments as well as the benefits. It may not be consistent with some of the other methods that we've discussed, especially around present worth, and present value. When do we normally use this? When's the best time to use it? When's the best situation? If payback time is measured in months and benefits continue for years, it might make sense. It's often used as a litmus test, gut check by startup enterprises. It's good for short-term analysis. Most projects with good payback periods look good on other measures, but not always, right? So therefore, payback can be unreliable for complex projects, long-range projects, etc. So, but it's an easy one to do. It's easy to explain. And many times companies and organizations use this in conjunction with other analysis methods, right? So look at the payback period here. You've got a cash flow situation, typical, negative in the beginning, positive in the years to follow. That's because there's an initial investment that takes away capital and then benefits that recoup in the years and periods that follow. So if you graph this, the payback period is when the two lines meet, right? When your accumulative benefits match your costs, right? So you can see also A has a smaller payback, has a payback period at a particular threshold, and alternative B is a different threshold at a higher value, but then it also happens a little bit quicker, 2.33 years versus 2.5 years. Here's another example. Pretty straightforward. Machine A provides the shortest payback period. I would encourage you to try this. Pause the video and try this for yourself. Here's a solution using a spreadsheet, using incremental present worth. We use the rate formula. We use the difference between one over the other. A new computer system costs $20,000. What's the savings? What's the payback? If I gave you the savings of $8,000, $4,000, and $3,000 for the respective years, be 3.5 years, because you figure out when you're going to recoup 20,000, and that's going to be roughly over 3 years, below 4 years, 3.5. There's a modified version of payback period. It's called discounted payback period. Anytime you see the word discounted, you imply an interest rate, which means that this now starts to take into account, it's a hybrid basically. It starts to take into account time value of money and applies it to payback. Does not have time value of money factored in. It computes the interest on cumulative investments, but it still is not the best. It's better because it does not factor in cash flows that follow after you recouped your investment, after the payback period has been achieved. Still ignores that. So, it's better, but not perfect still. Here's an example. You use NPER function to determine what the payback period is. A has a shorter discounted payback period if you take an interest rate of 10%. I is 10%. That means your money can earn 10% if you did nothing. So you're factoring in that time value of money for alternatives A and B. Sensitivity and break-even analysis are the next ones we want to just provide a quick overview of. What is sensitivity analysis? It is, when we talk about sensitivity, what are we sensitive on? We are sensitive on the uncertainties and any variations in data that might impact the decision that we're trying to make, right? How uncertain are the variables? And we can model different uncertainty levels.